this lecture video, we look at how to use Chebyshev's inequality to approximate probabilities involving an estimator of a population parameter. This is important because inference procedures that we'll be discussing in the future will be based upon such probability statements. The precision with which we can obtain these probabilities will depend on how much information we have about the distributions of the estimator. Our approach over the next several lecture videos will be to determine probabilities or approximations of those probabilities of events involving the estimators as progressively more and more information is available about their sampling distributions. We'll find that as more information about the distributions of an estimator becomes available, our probability assessments become more precise and more certain. In this lecture video, we begin this process by obtaining results requiring a minimal amount of information and as few assumptions as possible about these sampling distributions. In subsequent videos, we'll progress to situations in which we have more information about those sampling distributions, or for which more restrictive assumptions are required. We'll find that even in this very general situation, we can obtain useful information about probabilities of events involving an estimator of a population parameter. So here's an outline of what we'll be looking at in this video. We'll first discuss the process of estimation of a population parameter. We'll then describe events involving the unbiased estimator theta hat. We'll then look at an application of Chebyshev's inequality to probabilities involving that estimator theta hat. We'll state the inequality, and then we'll provide a relative frequency interpretation. So let's look at the process of estimating a population parameter. Let theta be an unknown population parameter of interest, about which we would like to make statistical inferences based on empirical data from the population. Let theta hat denote an estimator of the parameter theta calculated from the sample data. At their foundation, inference procedures about theta are based on probability statements involving the estimator theta hat. In particular, probability statements about the proximity of the estimator theta hat to the true parameter value theta. In order to obtain such probabilities, we need to know something about the sampling distribution of the estimator theta hat. The more information we have about the sampling distribution, the more accurate the probability statements about theta hat will be. This, in turn, will result in inference procedures about theta that are more powerful and more precise. An estimator theta hat, computed from a random sample, is itself a random variable, and its value varies from one sample to another. Loosely speaking, the set of all values that theta hat can take on, along with the probabilities of taking on those values, constitute the sampling distribution of the estimator theta hat. In other words, for a given method of sampling, the sampling distribution of theta hat is its probability distribution, and that probability distribution is induced by the particular method of sampling that has been used. Two important characteristics of the sampling distribution of an estimator about which we need information are its location and how spread out it is. The measure of location that we will be using is the mean. The mean has the physical interpretation as the center of mass of the distribution. It is the average of all possible values taken on by the estimator, weighted by their likelihood of occurrence. It is the value about which the estimator theta hat tends to vary from one sample to another. One way that we will denote the mean of the sampling distribution of theta hat is by the notation mu sub theta hat. The mean of the sampling distribution of theta hat is also called the expected value of the estimator theta hat, and this is denoted using the expectation operator notation, capital E, with the estimator theta hat in parentheses. So we have two ways of denoting the mean of the sampling distribution of theta hat, again also called the expected value of theta hat, and we will use both notations freely in these course notes. We will be using two closely related ways of measuring the spread of the sampling distribution of theta hat, the variance and the standard deviation. In words, the variance of the sampling distribution of theta hat is defined as the average squared difference between all values taken on by theta hat and the mean of its sampling distribution, mu sub theta hat. The variance will be denoted in two ways, by sigma squared sub theta hat and also using the var notation VAR with the estimator theta hat in parentheses. Note that the units of the variance of theta hat is the square of the units of the estimator theta hat. The standard deviation is defined as the positive square root of the variance. The standard deviation of theta hat will be denoted in two ways, by sigma sub theta hat and also by capital SD for standard deviation with the estimator theta hat in parentheses. The units of the standard deviation of theta hat are therefore the same as the units of theta hat. Finally, recall that another term for the standard deviation of the sampling distribution of theta hat is the standard error of theta hat. We'll be using both of these terms throughout these notes. Consider the process of estimation in general. What criteria might we use to evaluate the quality of an estimator? What properties might we expect an estimator to possess in order to be considered a good estimator? And finally, what qualities might we require of a sample statistic to be considered an estimator of a parameter at all? With these questions in mind, consider more specifically the sample statistic theta hat as an estimator of the population parameter theta, and let's think about their fundamental characteristics. The parameter theta is a constant. On the other hand, the sample statistic theta hat is a random variable, varying from one sample to another. Because of this, we would not expect the random variable theta hat to be equal to the constant theta in any particular observed sample. Therefore, it would not be a reasonable criterion to require equality of theta hat and theta in order to consider theta hat to be an estimator of theta. Nor would it be meaningful to use equality as a measure of the quality of theta hat as an estimator of theta. If equality of a sample statistic and a population parameter cannot be used to define what it means to be an estimator, what criterion can be used? Since theta is a constant, in order to make a meaningful comparison between a prospective sample statistic theta hat and the parameter theta for the purpose of defining what it means for a sample statistic to be an estimator, we need to identify some characteristic of the sample statistic theta hat that is constant and which can be meaningfully compared to the parameter theta. We find such a characteristic in the mean of the sampling distribution of theta hat. While theta hat is a random variable varying from one sample to another, the mean of its sampling distribution, mu sub theta hat, is a constant. It is the center of mass of the values taken on by theta hat, the value about which theta hat varies. Suppose first that the mean of the sampling distribution of theta hat is strictly less than theta. That is, that mu sub theta hat is less than theta. This implies that while theta hat does vary from one sample to another, on average, it tends to take on values that are less than theta. In other words, theta hat tends to underestimate theta. Next, suppose that the mean of the sampling distribution of theta hat is strictly greater than theta. That is, that mu sub theta hat is greater than theta. This implies that, on average, theta hat tends to take on values that are greater than theta. In other words, theta hat tends to overestimate theta. Finally, suppose that the mean of the sampling distribution of theta hat is exactly equal to theta. That is, that mu sub theta hat is equal to theta. In this case, it neither underestimates nor overestimates, on average, the parameter theta. When this is the case, theta hat is said to be unbiased as an estimator of theta. If a sample statistic is not unbiased as an estimator of a parameter, then it is said to be biased. Now, unbiasedness is an intuitively desirable property for an estimator. In the subsequent development, theta hat will be assumed to be an unbiased estimator of theta. Now let's look at some events involving the unbiased estimator theta hat. At their core, inference procedures about theta are based on probability statements about the proximity of the estimator theta hat to the true parameter value theta. Consider the following events involving the random variable theta hat. Theta hat takes on a value within k standard errors of theta. Theta hat takes on a value more than k standard errors away from theta. These two events are represented notationally and graphically on the following slides. The event theta hat takes on a value within k standard errors of theta can be represented notationally in a number of ways. For example, as the representation theta hat greater than or equal to theta minus k times the standard error of theta hat, and theta hat is less than or equal to theta minus k times the standard error of theta hat. It can also be represented by the second bullet point, where we see that theta hat is greater than or equal to theta minus k times the standard error of theta hat, and also less than or equal to theta plus k times the standard error of theta hat. And finally, we could represent this event notationally as theta hat being an element of the closed interval with left endpoint given by theta minus k times the standard error of theta hat, and upper endpoint given by theta plus k times the standard error of theta hat. Now note that because we're using square brackets to represent this interval, this is a closed interval. In other words, the endpoints are included. Now in the graphical representation below, the points on the number line that are within k standard errors of theta are shown in red. Note that the endpoints of the interval in red are, in fact, included. Next, let's look at the event that the estimator theta hat takes on a value more than k standard errors away from theta. Again, this can be represented notationally in a number of ways, as theta hat being strictly less than theta minus k times the standard error of theta hat, or that theta hat is greater than theta plus k times the standard error of theta hat. It can also be represented as the union of the two individual events, theta hat being strictly less than theta minus k times the standard error of theta hat, with the event theta hat greater than theta plus k times the standard error of theta hat. And finally, it can be represented notationally as theta hat being an element of the union of the open interval from minus infinity up to theta minus k times the standard error of theta hat, with the interval theta plus k times the standard error of theta hat as the lower endpoint and positive infinity being the upper endpoint. Now, in that last piece of notation, notice that each of those individual intervals, which we're putting together with a union, each of those is an open interval on both ends. And so neither endpoint is included on either of those individual intervals. Now below we have a graphical representation. And again, the points on the number line that are more than k standard errors away from theta are shown in red. Note that the endpoints of the intervals in red are not included. And so here we have a slide, just for your convenience, that puts those two graphical representations for these events on one slide. And so in the first number line, the points within k standard errors of theta are shown in red. In the second number line, points that are more than k standard errors away from theta are shown in red. All right, so now let's look at an application of Chebyshev's inequality to probability statements about the estimator theta hat. Chebyshev's inequality is a broadly applicable result that is typically covered in an introductory statistical methods course. We review it here because it can be used to approximate probabilities of events involving an unbiased estimator theta hat of a parameter theta when little is known about the sampling distribution of the estimator theta hat. All that's required is that sigma sub theta hat, the standard error of theta hat, be finite. Let k be any real number greater than 1. Applied to the unbiased estimator theta hat, Chebyshev's inequality states that the probability that theta hat takes on a value within k standard errors of the true parameter value theta will be no less than the quantity k minus 1 times k plus 1 over k squared. This is expressed notationally in the following way. The probability that theta hat is greater than or equal to theta minus k times the standard error of theta hat, and that it's less than or equal to theta plus k times the standard error of theta hat. That probability is greater than or equal to k minus 1 times k plus 1 over k squared. Applying the complement rule to this probability inequality, we obtain the complementary statement. The probability that the unbiased estimator theta hat takes on a value more than k standard errors away from the true parameter value theta will be no greater than 1 over k squared. In other words, the probability that either theta hat is less than theta minus k times the standard error of theta hat, or that theta hat is strictly greater than theta plus k times the standard error of theta hat, that probability will be no more than 1 over k squared. Notice the following two important points about Chebyshev's inequality. Chebyshev's inequality applies to any unbiased estimator that has a finite standard error. The estimator's sampling distribution does not have to be Gaussian. That is, it does not have to be a normal distribution. In fact, it does not even have to be symmetric. The sampling distribution could be highly skewed, it could be heavy-tailed, it could be multimodal. As long as the standard error, sigma sub theta hat, of the estimator theta hat is finite, Chebyshev rule applies to that estimator. The second point, these inequalities provide guaranteed bounds on the associated probabilities. The next slide contains values of these guaranteed bounds on these probabilities for various values of k. And so in the first column, we have various values of k, and notice that we have k values greater than 1, which is required for the application of Chebyshev's inequality. In the second column, we have guaranteed lower bounds on the probability that the unbiased estimator theta hat is within k standard errors of theta. And in the third column, we have guaranteed upper bounds on the probability that the unbiased estimator theta hat is more than k standard errors away from theta. So for example, if we look at the row for k equal to 2, we see that the probability that the unbiased estimator theta hat takes on a value within 2 standard errors of the true value of theta, that probability is guaranteed to be at least 0.75. The complement of that would say that the probability that the unbiased estimator theta hat takes on a value more than 2 standard errors away from the true value theta is no more than 0.25. And that is guaranteed. Using a value of 4 for k, we see that the probability that the unbiased estimator theta hat takes on a value within 4 standard errors of the true value of theta is guaranteed to be at least 0.9375. The complement of that says that the probability that the unbiased estimator theta hat takes on a value more than 4 standard errors away from theta is guaranteed to be no more than 0.0625. And if we use 5 as a value for k, we see that the probability that the unbiased estimator takes on a value within 5 standard errors of the true value theta is guaranteed to be at least 0.96. The complement of that says that the probability of getting a hold of a sample for which the unbiased estimator theta hat takes on a value more than 5 standard errors from theta is guaranteed to be no more than 0.04. So now let's provide a relative frequency interpretation for these probabilities. In repeated sampling, the estimator theta hat will take on a value within k standard errors of the true parameter value at least k minus 1 times k plus 1 over k squared times 100% of the time. The complement of that says that the random variable theta hat will take on a value more than k standard errors away from the 2 parameter value of theta, no more than 1 over k squared times 100% of the time. Now again, note that k can be any real number greater than 1, and these bounds are guaranteed. And so let's look at some examples. In repeated sampling, the random variable theta hat will take on a value within 2 standard errors of the true parameter value theta at least 75% of the time. It will take on a value within 3 standard errors of the true parameter value theta at least 88.89% of the time. Theta hat will take on a value within 4 standard errors of the true parameter value theta at least 93.75% of the time. It will take on a value within 5 standard errors of the true parameter value theta at least 96% of the time. And theta hat will take on a value within 6 standard errors of the true parameter value theta at least 97.22% of the time. And again, these bounds are guaranteed. Looking at the complement of these statements, in repeated sampling, the estimator theta hat will take on a value more than 2 standard errors away from the true parameter value theta, no more than 25% of the time. Theta hat will take on a value more than 3 standard errors away from the 2 parameter value theta, no more than 11.11% of the time. It will take on a value more than 4 standard errors away from the 2 parameter value theta, no more than 6.25% of the time. Theta hat will take on a value more than 5 standard errors away from the true parameter value theta, no more than 4% of the time. And finally, theta hat will take on a value more than 6 standard errors away from the true parameter value theta, no more than 2.78% of the time. And again, these bounds are guaranteed, and this is applicable for any population or any sampling distribution of an estimator for which the standard error of that sampling distribution is finite. So this result, Chebyshev's inequality, and its application to sampling distributions of estimators and corresponding probabilities about the estimators, applies in a wide variety of situations. So that's what I wanted to show you in this lecture video. I'll see you in the next lecture video.